So today's lecture is all about regularity, measurable functions. So in regularity, what we are going to do is that a given measurable set E can be approximated, by open set, by closed set, by G delta set, and by F sigma set. By approximation, what we mean is that if we have a positive number, if we take an arbitrary positive number epsilon, how small it may be, okay, so we can take an open set O that is containing the measurable set E such that outer measure of the E difference or O difference E is less than equal to epsilon. Okay, so that is what about the approximation of a measurable set by an amount of epsilon by an open set like that. So this is all about approximation of a measurable set by open set, by closed set, by G delta set, and by F sigma sets. So yeah, let us see regularity. So we are going to prove some important result here. The following statements regarding the set E are equivalent, right? So E is measurable. Number one statement is E is measurable. And then, number two statement, for every epsilon positive, there exists an open set O containing E such that outer measure O difference E is less than equal to epsilon. So this is about approximation of this measurable set E by an open set O. So the approximation is error is epsilon, less than epsilon, like that. All right. So number three statement, there exists a G delta set, and that is a superset of E such that outer measure G difference E is exactly equal to 0. So in this situation, the outer measure of G difference E is exactly equal to 0. And number four statement, for all epsilon positive, there exists F, a closed set, and that is contained in E. So this closed set is inside E such that outer measure E difference F is less than equal to epsilon, right? So this is statement number 4. So statement number 5, there exists F, a F sigma set, and that F is a subset of E such that outer measure E difference F is exactly equal to 0. All right. So we are going to prove these statements, equivalence of this statement. So what we are going to do is that 1 implies 2, 2 implies 3, then 3 implies 1, so then 1 implies 4, 4 implies 5, then 5 implies 1. So that is the the method we are going to use here. So let us prove it. 1 implies 2. Suppose outer measure of E is finite. So measure of E is measurable, so outer measure and measure are equal, so you can drop star here, and E is less than infinity. Then for every epsilon, there exists an open set O that is containing E, that we have done that one. So such that outer measure O less than equal to measure E plus epsilon. So from here you can write measure O difference measure E, that is exactly equal to measure O difference E is less than equal to epsilon. All right. Since open set is measurable, you can drop here and star here, and E is given that measurable. Therefore, you can also drop star here. So this is equal to M O difference E because O is a superset of E, and that is less than equal to epsilon. So that is what we are now able to prove for the case when measure of E is finite. And then suppose a measure of E is not finite, that is infinity. We can write R in this form, union, countable union, and going from 1 to infinity In, a union of disjoint finite interval. So this is a union of finite disjoint interval, means In is a finite interval, and all of their union is exactly equal to R. All right. So you can put En is equal to E difference In. So the intersection E intersection In is equal to En. So since In is finite interval, so therefore a measure of En is also finite. All right, in are measurable, E is measurable, therefore En is also measurable and its measure is finite. All right, so there exists an open set On. So by using the case number 1, we can find an open set On that is containing En such that measure On difference En is less than or equal to E divided by 2 to the power epsilon. This is coming from the case 1 when the measure is finite. We can use that case because measure of En is finite. For this measurable set En, we should be able to find an open set On containing En such that measure On difference En is less than or equal to epsilon by 2 to the power n. Alright, so then we can write O is equal to union n going from 1 to infinity On. So each open set On is open, therefore their union is also open. So O is an open set, and O difference E we can write in this form: union n going from 1 to infinity On, difference union n going from 1 to infinity En, and that is a subset of union n going from 1 to infinity On difference En. We can write in this form. So by subadditivity, subadditivity formula, we have measure O difference E is less than or equal to summation n going from 1 to infinity measure O difference En, that is less than or equal to summation n going from 1 to infinity epsilon by 2 to the power n, and this is a geometric series, its sum is epsilon. Alright, so ultimately this is less than or equal to epsilon, where O is open set and O is a superset of E. Okay, that is what we wanted to prove. Next, 2 implies 3. Statement number 2 implies number 3. For this n, let On be an open set. By statement number 2, for every epsilon there should be an open set containing E such that m star On difference is less than or equal to epsilon. So instead of taking epsilon, you can take 1 upon n, the reciprocal small number. So for a given positive natural number, for a positive integer n, we should be able to find an open set On containing E such that outer measure On difference E is less than or equal to 1 upon n. Right? Then you put G is equal to this countable intersection n going from 1 to infinity On. So then G is in a G delta set. Okay, and each On is a superset of E, therefore G is also superset of E. Alright, so then G is a superset of On for each n, so G difference E is a subset of On difference E. So G difference E is a subset of On difference E. Alright, it follows that m star G difference E is less than or equal to m star On difference E, that is less than 1 upon n for its n. Alright, so here we are writing star because we don't know whether E is measurable or not. So On is measurable. Since E, we don't know the measurability of E, On difference E is measurability, we don't understand. Therefore, we are still writing m star here. Here also we are writing m star because we don't know the measurability of E. We are assuming statement 2. Alright, so this is true for each n. This is true for each n. Alright, therefore, as n tends to infinity, so you are going to get m star G difference E, because m star G difference E, it is an outer measure, it cannot be negative, therefore it should be 0. So m star G difference E is exactly equal to 0, and that is what we wanted to prove, the statement number 3. Alright, so now let us prove statement number 3 implies statement number 1. 3 implies 1. So we are assuming 3, and then we are going to prove, that is, we are going to show that E is measurable. Alright, provided m star G difference E is equal to 0, we are going to show that E is measurable. So there exists a G delta set G such that G is a superset of E and m star G difference E is equal to 0. This is, statement number 3. We are going to assume this one, and then we are going to prove that E is measurable. So from here it follows that G and G differences are measurable set, because we have already shown earlier that if the outer measure of a set is 0, then the set is measurable. Since outer measure of G difference is 0, so G difference is measurable. But G is a G delta set, therefore G delta set G is also measurable. That is, G and G differences are measurable set. So therefore, you can write E in this form. E can be written in this form: G difference E, and this is measurable, this is measurable. Difference of two measurable set is measurable, so E is measurable, and that is what we wanted to prove. So next, let us try to prove statement number 1 implies number 4, that we are going to assume that E is measurable, and then we are going to show that statement number 4. So E is measurable, so therefore its complement is also measurable, that is EC is measurable. Alright, so there exists an open set O such that O contains the complement of EC. Alright, so that we have already shown that one. There exists an open set O containing EC, and measure O difference EC is less than or equal to epsilon. So this we can assume. Next, O difference EC you can write in this form: O intersection complement of EC, and that is exactly equal to E intersection O, and that is you can write in this form: E intersection O complement, that is E difference O complement. Alright, so O difference EC you can write O difference OC, and therefore measure, because E is measurable, EC is measurable, open set O is measurable, so O difference EC is measurable. Therefore you can drop here M star you can drop here. M O difference EC is exactly equal to M E difference OC, and since this is equal to M E difference F. Alright, so it's less than or equal to epsilon, where F is equal to OC. Instead of O complement you can write F. Okay, and then since O is open, F is a closed set. Right, so and that is what we are now able to prove statement number 4. Now assuming statement number 4, we are going to prove statement number 5. So for each n we should be able to find a closed set Fn, so such that Fn is a subset of E, and M star E difference Fn is less than 1 upon n. Here also we are not dropping star because we don't know the measurability of E. Fn is measurable, but we don't know the measurability of E. E may be measurable or not measurable. Therefore M star we are using star here. So M star E difference Fn, this is from number 4. M star E difference Fn is less than 1 upon n. Right, so then you put F is equal to this countable union and going from 1 to infinity Fn, and then F is an F sigma set, and F is a subset of E also, because if Fn is a subset of E, therefore their union is also subset of E, that is F is a subset of E. So E difference F you can write in this form: E difference F is a subset of E difference Fn. So outer measure E difference F is less than or equal to outer measure E difference Fn, and that is less than 1 upon s for each positive integer n. Alright, so as n tends to infinity, what we are going to get is that outer measure E difference F is less than or equal to 0, but it cannot be negative, therefore it should be 0. M star E difference F is exactly equal to 0. So that is what we wanted to prove. We are able now to prove number 5. So next we are going to prove number 5 implies 1, and that completes the proof of the theorem. There exists a F sigma set F such that F is a subset of E, and M star E difference F is exactly equal to 0. Right, so this is the statement number 5, and now we are going to show that E is measurable. So again, F is measurable, it has been given, and since outer measure of E difference F is equal to 0, E difference F is measurable. Right, so then since E can be written in this form: F union E difference F, E is measurable, E difference F is measurable, therefore F is measurable, E difference F is measurable, therefore E is also measurable. Alright, so it completes the proof. Next, let us define definition of a measurable function. What is a measurable function? We have defined a measurable set. So many theorems we have proved about the measurable set. Now let us come to the measurable function. Alright, let F be an extended real valued function defined on a measurable set E. Alright, the function F is defined on a measurable set E, and the function is extended real valued function, means it can take positive infinity and negative infinity also. Alright, so then f is a Lebesgue measurable function, or more briefly a measurable function. So it is called Lebesgue measurable, or simply and briefly we can say that measurable function if the following condition fulfilled. If for each alpha, for every real number alpha, the set x such that f of x is greater than alpha is measurable. Okay, the collection of point x such that f of x is strictly greater than alpha, and that is a subset of R. If that subset of R is measurable for each alpha, then we say that the function f is measurable. All right. So let us see some illustration of this one. Suppose the graph of the function is this one. Suppose the graph of the function is this one, and suppose alpha is exactly equal to 2. Then the value of x such that f of x is greater than 2 is, so this one 2 is this horizontal line, and f of x here is well above this horizontal line, that is 2, and the point will be here. So the point x here, f of x will be here. So that point will give you f of x that is greater than 2. Therefore, from the graph it is obvious that any point in E1, then its f of x will be greater than 2. So similarly, any point here in the E2, f of x will be greater than 2 here, because they are above the the line x is equal to 2. All right. So therefore, x such that f of x is still greater than 2. So what are the point? Those are the point in the union E1 E1 union E2. All right. So the definition says that the set x such that f of x is strictly greater than alpha is measurable for its real number alpha. I am just giving for the case when alpha is equal to 2, but the definition says that it should be, the set should be measurable for its real number alpha, and then only then we can say that the function f is a measurable function. All right. So, and that is the illustration. Now let us prove some important theorem. The following statements are equivalent. Number 1, f is measurable. Number 2, for every real number alpha, the set x such that f of x greater than or equal to alpha is measurable. Number 3, for every real number alpha, the set x such that f of x is strictly less than alpha is measurable. All right. Number 4 statement, for every real number alpha, the set x such that f of x is less than or equal to alpha is measurable. All right. So all these statements are equivalent. Okay. Let us prove it. 1 implies 2. Let f be a measurable function. Okay. So one can write x such that f of x greater than or equal to alpha. You can write this set as a countable intersection n going from 1 to infinity, x such that f of x strictly greater than alpha minus 1 upon n. Okay. So this set you can write in this form. Since the function f is measurable, this set is measurable for each n. So that countable intersection of measurable set is measurable. So since this is measurable and this is measurable. Okay. So it is nothing but to express this set. We don't know the measurability of this set, but if we are able to show that this set can be expressed as a countable intersection of measurable set, then this is going to be measurable, and this set is exactly equal to countable intersection of this measurable set. Why this is measurable? Because of the definition of f. All right. Since f is measurable, this set is measurable. All right. So it is very simple that this set is measurable. Okay. Therefore, this is measurable. Next, 2 implies 3. Suppose x such that f of x is still greater than alpha is measurable for all alpha. Right? The complement of this set. What is the complement of this set? The complement of this set is x such that f of x is still less than alpha. The complement is measurable. Okay. So complement of this set is measurable. Therefore, this set is measurable. So we know that x such that f of x is greater than or equal to alpha. Complement is exactly equal to x such that f of x is strictly less than alpha. All right. So since this set is measurable, therefore its complement is also measurable. That is, this set is measurable. All right. So this is measurable. Okay. Number 3 implies 4. Suppose that the set x such that f of x is strictly less than alpha is measurable for its alpha. This set is measurable for its alpha. All right. We can write x such that f of x less than or equal to alpha in this countable intersection form, intersection n going from 1 to infinity x such that f of x is less than alpha plus 1 upon n. All right. So therefore this set is also measurable. Okay. Then for implies one. Suppose for if for all alpha in R, the set x such that f of x is less than or equal to alpha is measurable. All right. So its complement is also measurable. What is the complement? The complement is x such that f of x is strictly greater than alpha is measurable. All right. Since this set is measurable, its complement is measurable. So this set is measurable. This is measurable for every alpha. Therefore, the function f is measurable. Okay. And that is what we wanted to prove. So some example, let us see. So that if f is measurable, then x such that f of x exactly equal to alpha is a measurable for its extended real number alpha. So this is very interesting example, the first example of measurable function. Let us see. We know that for a finite alpha, x such that f of x exactly equal to alpha, you can write in this form x such that f of x is greater than or equal to alpha, intersection x such that f of x is less than or equal to alpha. We have just now proved that this set is measurable whenever f is measurable, and this is also measurable. So the intersection is nothing but exactly equal to x such that f of x is exactly equal to alpha. Therefore, intersection of two measurable set is measurable. So this set is measurable. Okay. Whether the set on the right hand sides are measurable, therefore this set is measurable. That is the case when alpha is finite. For alpha equal to infinity, one can write x such that f of x is exactly equal to alpha infinity. You can write in this form, intersection n going from 1 to infinity x such that f of x is greater than n, for its n. So this is measurable for its n. All right. Therefore this is also measurable. So for alpha is equal to minus infinity, one can write x such that f of x is equal to minus infinity is equal to n, intersection n going from 1 to infinity x such that f of x is strictly less than minus n. Hence the reason follows. Okay. Then constant functions are measurable. All right. So let f of x is equal to c be a constant function. Okay. And then let alpha be a real number. All right. So if alpha is less than c, then x such that f of x is greater than alpha is exactly equal to e, which is a measurable set, because e is a measurable set. So if alpha is greater than or equal to c, then x such that f of x is greater than alpha is equal to phi, and then domain of definition of f. Okay. The domain is phi. This empty set is measurable. Okay. Therefore f is measurable. All right. So next is another example. The characteristic function chi a of a set A is measurable if and only if A is measurable. All right. So chi a will be measurable if A is measurable. Conversely, if A is measurable, then chi a will be measurable. All right. So recall the definition of characteristic function chi a. It is defined by, it is a real valued function from R to R defined by this formula chi a, so is 1 if x is a member of A, it is 0 if x is not a member of A. All right. So if alpha is less than 0, then x such that f of chi a x greater than alpha is equal to R. So if alpha is greater than or equal to 0 but less than 1, then x such that chi a x is still greater than alpha is exactly equal to A. All right. If alpha is greater than or equal to 1, then x such that chi a x is still greater than alpha is empty set phi. So empty set phi is measurable, R is measurable, then chi a will be measurable if A is measurable. All right. So therefore chi a is measurable if A is measurable, if and only if A is measurable. So it proves the example. Then next, let us show that continuous functions are measurable. All right. So for alpha in R, we have x such that f of x still greater than alpha is exactly equal to x such that alpha f of x is in between alpha and infinity. This is an open interval, and open interval is measurable set. All right. So this is x such that f of x belongs to alpha infinity, this open interval, and that is inverse image of alpha infinity. Since f is continuous, its inverse image is open. So every open set is measurable, that we have already shown. Since f is continuous, this is an open set, and therefore this one is measurable for its alpha. All right. So yeah, so what we do is that we are converting the given set into in terms of the measurable set, either the difference of measurable set, union of measurable set, intersection of measurable set. That is the method we use here. So we want to prove the measurability of a given set, and we try to convert the set in terms of the union of measurable set, intersection of measurable set, and difference of measurable sets. So if we are able to do that one, then simply we are able to prove that the set is measurable. That is what we have done so far. All right. So another example, let f be an extended real valued measurable function defined on a measurable set E. All right. So then f plus c and then cf are measurable for any c. All right. So f is measurable, f plus c is another function. So we are going to prove the measurability of the f plus c. F is measurable, then we are multiplying the f by c, and cf is a new measurable function. We are going to prove that one. All right. So proof for each alpha, we are going to prove x such that f of x plus c is greater than alpha is measurable. But this set is exactly equal to x such that f of x is greater than alpha minus c, and this is another real number. Since f is measurable, this set is measurable. That is, this set is measurable for any alpha. Therefore, the function is measurable. The right hand side is measurable for its alpha. All right. So therefore, f plus c is measurable function. Okay. And next, if c is equal to 0, cf is equal to 0, a constant function. We have shown that constant function is measurable. So in case c is equal to 0, cf is measurable. All right. Therefore, cf is measurable in this case. Okay. If c is greater than 0, then for its alpha we have x such that cf still greater than alpha is equal to x such that f of x is still greater than 3 inverse alpha. All right. So since f is measurable, this is measurable, and that is this is measurable for every alpha. Hence cf is measurable in this case also. So if c is less than 0, then for each alpha we have, you can write x such that cf x still greater than alpha. You can write in this form x such that f of x is still less than c inverse alpha, because c is negative. So you can write in this form, but this set is measurable because f is measurable, and that is this is measurable. Okay. Therefore cf is measurable in this case also. So that is the method we use. I already told you we are trying to convert the unknown set in terms of the measurable known set. Okay. That is the method we have used so far.